Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to see some of the basic mathematical background which we may require during course of study. So, here I am going to talk about some basic concepts of linear algebra, calculus, probability and statistics, and graph theory and search algorithm, and the complexity analysis. So, here we will be covering up these topics as just said, and you will be able to learn some of the basic concepts of these topics, and we will be studying these topics further in detail as well as some other topics during the course of the lecture. So, first of all, let us see that if I have to represent say a point in space, okay, or say if I have to represent the tip of a robot in space, how can I do that? Okay. So, to do that naturally I need to have a coordinate system say x, y here, and suppose if this point P I want to represent, I can represent that with the help of a vector, okay, which contains information about x tip and y tip, okay. And this vector is nothing but it is a ordered sequence of values, okay. And in robotics we usually represent it by a column vector or a transpose of a row vector, okay. And some of the basic vector operations as you might have studied in your earlier classes such as vector addition, where we sum two vectors by adding up the individual components of the two vectors. Here we do the scalar multiplication again by multiplying with scalar to all the components of the vector, and we define the dot product as the magnitude of those two vectors into the cosine of the angle between the vectors, okay. And we also define the norm of the vector, okay. So, this way it is done, and as I said we can represent the position of the robot tip or any other position vector of any other joints of the robot or any point in the robot link using the vectors. Let us see about matrix, okay. So, a matrix is nothing but it is a rectangular array of elements arranged into say m rows and n column, and if your m and n are 3, then I can write this matrix like this, okay. So, here this is the first row, second row, third row, and these are the first column, second column, third column, and accordingly we put with the elements these subscript first row first column, second row first column, say second row second column, like that we can do that, okay. And we define the transpose of a matrix by interchanging rows and column, okay, as it is done over here. So, I can write these rows, okay, as the column over here, alright, and this way I can define the transpose for all, okay. And identity matrix is a square diagonal matrix with ones on the diagonal and zeros elsewhere, and it satisfies, that is, if you multiply a matrix with the identity matrix you are going to get the same matrix. Symmetric matrix is a square matrix where the matrix is same if you take the transpose of the matrix. We use this matrix concept, okay, to represent the mass distribution and inertia tensor of a rigid link in order to calculate the dynamic forces. There is a special class of matrix what we call as the skew symmetric matrix, okay, and this skew symmetric matrix is a square matrix where S is equal to minus of S transpose, and it has 0 diagonal elements. In robotics, we use this this concept in order to represent a vector cross product as the product of a matrix and a vector, okay. So, for example, say if your vector omega is defined like this, I can define a skew symmetric matrix S here, where with the diagonal elements 0 and the other elements shown like this. Now, if I take a cross product, okay, vector cross product of this omega with P, okay, having say the x, y and z component, okay, say px, py and pz, Okay. So, this vector cross product is going to be equal to the matrix multiplication of this S skew symmetric matrix and the vector P. Okay, and this is very much convenient to us when especially we are trying to find out the how the velocities propagates from one link to next link, and those things we will be seeing in our coming lectures. Okay, next important concept is the matrix multiplication. The product, as all of you must be knowing, the product AB is defined only if the number of columns in A is equal to the number of rows in B. Okay, and it is associative, that is you can form association here say this way, but they are non-commutative, that is AB is not equal to BA. And compounding of this matrix multiplication basically is very much useful when we are trying to find out the transformation matrices, okay, using a DS parameter, okay, in order to find out the final position and orientation of robot and effector, say with respect to the base frame, okay, or the inertial frame. Next concept which we are going to look at is the determinant, rank and the matrix inverse. The determinant, as all of you know, is a single number, what we call as a scalar, which is calculated from a square matrix. It tells whether a matrix is invertible or not, and it acts as a scaling factor for the linear transformation. And rank is defined as the maximum number of linearly independent rows or column in a matrix. The matrix inverse exists only if determinant of matrix is not equal to 0, okay, and it satisfies basically A inverse is equal to the identity matrix. There is a concept of singularity, and that concept says that a singularity occurs if the Jacobian matrix loses rank, okay, that is the determinant of Jacobian becomes 0, making the inverse impossible to compute. And we use this concept when we are trying to find out the joint rates, okay, given the end effector velocities. Okay. So, that mapping, in that mapping we use this concept of the matrix inverse, okay, and this is given as A inverse as 1 by determinant of A into adjoint of A. Adjoint of A, how these are calculated, maybe you can refer the standard maths textbook, you will get the information of that. Next concept is the eigenvalues and eigenvector. For a square matrix A, eigenvector x non-zero vector that satisfies say Ax is equal to lambda into x, where lambda is the eigenvalue. From this equation we get the characteristic equation basically, that is determinant delta I, where I is identity matrix into A is equal to 0. They represent the principal direction and scaling factor of a linear transformation, and this concept is used in robotic control system to see whether your system is asymptotically stable or not, okay. And if the real part of the eigenvalues of the system matrix all negative, then we say that it is asymptotically stable. Next concept is gradient of a scalar function. Okay. So, this concept is very much used in robotics when a robot has to travel say an environment in order to reach the goal, and where in the environment many obstacles are present. Okay. So, there we use this concept. So, for a scalar value function, a vector x, okay, where this function is mapped from n dimensional real number space to a say singular number in the real space, the gradient is vector of partial derivative of the function with respect to each element of the input vector. Okay. So, you have del f by del x1, del f by del x2 and so on, and that is what we define as the gradient of fx. And as I said, they are used to navigate the potential fields, okay, where a robot is attracted to a goal and repelled by the obstacle, which forms the foundation of the planning algorithm. So, if you look at this figure, say this is your goal and this is your obstacle, then values of this function reduces as you go nearer to the goal. but whereas if you have an obstacle, then values of this gradient is very high value. Okay. So, that way we can identify the obstacle and we can have the path planning for a robot. Next concept is the time derivative of vectors and matrices. So, if you want to take the derivative of a matrix or a vector, naturally you have to take the derivative of the each element of that matrix or vector. Okay. So, that is what it is, and its concept is used in robotics. We use for a rotation matrix, the derivative is given by S omega into R, where our S omega is a skew symmetric matrix representing the angular velocity. Okay. Now, let us move on to some of the basic fundamentals of the probability theory. Okay. So, which are very much used in our robotics and AI course. So, let us have a look at the definition. This probability, as you know, is a measure over a set of events, okay, satisfying a specific axiom that quantify the likelihood of an outcome. Okay. So, these axioms are that probability of an event x being less than equal to xi, that is always going to lie between 0 and 1, and sum of the probabilities of likelihood of x being xi, okay, is going to be equal to 1. An experiment is a well defined process of observation and the sample space may be discrete. For example, you could have the countable outcomes or continuous one where you have the uncountable outcomes. Okay. So, the use of this concept is in knowing the likelihood of robot encountering a specific state in a discrete environment before taking any action. So, if you look at this figure, okay, so suppose this is a room of your house, okay, and here this is the position of the robot, okay, and you have the obstacles, say some obstacles are here, say walls are there or your tables are there. So, for the robot to move on, there are only 4 places possible. Okay. So, the probability here for the each one is going to be 1 by 4, that is 0.25, and sum of the probability is going to be equal to 1. So, that way both the axioms are satisfied. Okay. Next, let us look at the concept of conditional probability. Conditional probability is the updated likelihood of an event A given event B has occurred. Okay, and this is the foundation of Bayesian statistics, which measures degree of belief. Okay. So, the probability of event A to occurring considering the event B has already occurred is probability of event B occurring given the event A has occurred into the probability of event A to occur divided by the probability of event B to occur. Okay. The prior probability represent belief before evidence. Posterior probability represent belief after updating with the new evidence. Okay. And these concepts we can use for the localization. Okay. For example, estimating robot state X given a model and noisy sensor measurement Z. Okay. So, here I am given the sensor measurement Z and I am interested in locating the state of the robot, okay, by the state X. So, that I can represent by the conditional probability. Then we can also use this concept in decoding in speech recognition. Okay. So, finding the word sequence say I that best explains the observed audio signal O is again can be given this way. Okay. Next, let us look at the random variable, concept of random variable. Okay. So, a random variable x is a function basically which maps from say omega to the real number space R, okay, and that maps experimental outcome to the real number, and this we can define the expected value, okay, for the say discrete events. Okay. So, expected value will be actually the summation of these individual event into probability of that individual event to occur. Okay. So, this is for the discrete one, And similarly for the continuous one, I can give the expected value for event x to occur as integral from minus infinity to x infinity that event into the probability density function. Okay. So, that way we can do that. The discrete random variable use a probability mass function while the continuous variable use the probability density function. Okay. And we use this concept in calculating the expected reward a robot receives in Q-learning, okay, based on a weighted average of the potential future rewards for a specific action. We will be seeing these things much more detail when I will be talking about the reinforcement learning. Then we have the binomial distribution model. It models the number of success in a series independent Bernoulli trials. Okay. So, that is given by say probability for r number of events to occur as n choose r, out of n we choose r say, into the probability of the success of the event to occur to the power r into the probability of failure to the power n minus r. And we use this concept in the natural language processing, where estimating the probability of observing a certain number of sentences containing transitive words by treating each sentence as say an independent yes or no trial. Okay. Then next is the Gaussian or the normal distribution. We are very much aware of this concept as we have been using so long. So, a continuous distribution defined by say a mean mu and standard deviation sigma forming a bell curve, okay, and this is given by this expression. And it is used in the modeling of the SLAM basically, which is nothing but simultaneous localization and mapping, and modeling process noise and measurement noise in a Kalman filter. Then the maximum likelihood estimation finds the parameter values that best explain the observed data only, okay, and a maximum a posteriori estimation improves this maximum likelihood estimation by incorporating prior knowledge about the parameters. Okay. So, this MAP can be given by the argument of max of this probability, okay, where this mu m by s is the probability of the model given the observed data or say signal s, okay. And again this we can similarly define these probabilities P s for the given mu m, that is likelihood of sensor measurement, that is the probability of observing signal given the model mu m is true, and similarly pi mu m is the prior belief about the parameter, that is the probability of the model mu m before seeing the data s, and Ps is the total probability of the data s across the all possible models. In this Bayesian updating, what we do is that begin with an initial belief, okay, and each new sensor observation update this belief, and then the updated belief becomes the new initial belief, okay, and that is how we go on doing this Bayesian updating. I can give you an example related with the robot sensor where we are going to use this concept, okay. A mobile robot estimates its say distance to a wall, okay, using say a noisy range sensor. Then MLE will estimate distance using only the latest measurement, whereas my MAP combines new measurement with the prior knowledge, that is we may have some map information. As more sensor data arrives, the robot estimates become more accurate and stable. Bayesian estimation allows robots to continuously refine sensor based estimates by combining data with the prior knowledge. Next, let us look at the concept of entropy. Okay. Entropy is a measure of average uncertainty on the information content of a random variable, and this entropy say of x is given by summation of multiplication of probability for that x event to occur into the logarithmic of that probability. okay, and this entropy relates to surprise. Higher surprises indicates higher entropy, and it is used to measure the quality of the robotic model. Okay, better model captures more structure and thus have the lower entropy. Now, this concept we use in decision trees, and in decision trees entropy measures the impurity of the data split to determine the most informative feature of the robot classification task, which we will be seeing. Next is the state space equation. We will be using these equations in the robot control, okay, and the state space representation of a linear time invariant, which we often call as LTI system, that is basically given by these two equations, okay. So, that is the state's derivative is equal to say matrix A into xt plus b ut and the output equation. So, this is the state equation and the output equation yt is given by c into xt. Okay. Here ut is the basically the input. Okay. So, this way basically what we do is that we represent the or we break down the higher order differential equation into the first order equations. Okay. And this concept is used in the dynamics of a robot arm, where your xt represents the position and velocity. Next, let us look at some of the concept of the graph theory. Okay. A graph is an abstract mathematical representation of a set of objects connected by links or edges, okay, and these are denoted as G is a set of V and E, that is vertices and the edges. Okay. Edges can be directed, indicating one way traversal, or undirected, represents the weight or cost to move between the nodes, and we can have a sequence of edges from one node to another that constitute a path, and path starts and end at the same node, then what we call it as the cycle. Okay, it starts and end at the same node. A tree is a specific type of connected directed graph that contains no cycle and has a root node. The path cost we can find out as sum of the weight of all edges in a sequence. Okay. So, representing a factory floor as a graph where nodes are say docking station and edges are the safe passages for a mobile robot. Okay. So, in this example, say this is dock 1 and this is dock 6. Okay. Say the mobile robot has to pass from dock 1 to dock 6, and there are say two ways possible. One is say this way and say another is this way. Okay. Now, and say this way is mobile robot cannot pass. Okay. Other way could also be say from here to here, and then it goes like this way. Okay. So, in this problem our aim is to find out that minimizes the total traversal cost. Okay. So, the aim here is to find out a path that minimizes the total traversal cost. So, if we look at here in this, if it follows this path, then cost will be 2 plus 3 plus 1. Okay. So, this is going to be the minimum cost path. Okay. So, this way we can represent it using graph theory. Uninformed search explores a graph without any preference for the goal location, relying solely on the graph structure. There are two types of searches possible. One is the width first search, and the width first search explores all nodes at a specific link length. Okay. The number of edges from the start before moving deeper. Okay. So, for example, here if we look at this graph, so say this is your start, and if G is the goal and you have to perform the width search, then say from start S it will go to A, it can go to B, it can go to A, okay, and then from A it can go to C, it can go to D like that, and from C it can go to F like that, okay, and from B it can go to E and it can go to H like that. Okay. So, the shortest path, the fewest edges that we can identify using this graph. Okay. And this concept is used in a queue, that is first in first out, okay, and it guarantees to find the shortest path in terms of the number of edges, not in terms of the distance or cost. Likewise, we can define the depth first search, okay, and in the depth first search it explores a path as deeply as possible before backtracking to unvisited children, okay. And so in this figure, if you look at, okay, so from S, say we are going to A, then it will explore, okay, is there connection with B? No. Is there connection with C? Yes. So it will follow the path C, okay, like this, okay. Then when it reaches C, it will say that is there connection with A? It is already covered. Is there connection with B? No, that is not there. Is there connection with D? It is again not there. Is there connection with E? No, it is not there. So is there connection with F? So it will pass to the F. Likewise, we can identify the path to reach till the goal point, and this is implemented using a stack format, which is the last in first out, okay, and it is often more memory efficient in deep graphs, okay, but does not guarantee an optimal path. Okay. The highlighted DFS here is the first solution found. It is not necessarily, as I said, that it is the optimal solution, okay. So the DFS is the fast for exploration, whereas the BFS is better when the shortest path matter. A search tree represents a sequence of decision basically, okay. So we have internal nodes which questions test an attribute, say is the surface is of glass or not. We have the branches, whether it tells the outcome of those tests, whether yes, no, high, low. We have the leaf nodes in a search tree which tells the final decision or classification, whether the object is fragile or sturdy. Okay. So this structure mirrors how decisions are made step by step. We will be seeing these things much more detail when we will be looking at the path planning of the robot. Okay. So they are commonly used for classification tasks where sensor data must be mapped to an action or level. Okay. So decision trees, one explicit of the decision rule they use, and there is another method called random forest where many decision trees combined for the robustness. So here the goal is to reduce uncertainty using entropy. And entropy, as we have defined, this can be defined like this. I have defined in the previous slides. If the robot is unsure whether an object is fragile or sturdy, entropy is going to be high. Okay. And the information gain is, we can calculate basically the entropy of the parent minus summation of the probability of the child into entropy of the child. Okay. So that we can get. The robot chooses the attributes that gives the largest reduction in entropy. This determines the order of questions in the tree. A robot arm classifies an object as fragile or sturdy using visual sensors. Okay. So this is just an example. So if your surface is glass, so it is fragile, so apply a low grass force. Else check other properties, whether thickness, okay, decide grass force. This explicit decision logic improves safety, interpretability and the control. So that is what is concept here using decision tree. Is the surface glass? If yes, then it will ask whether fragile. If it is yes, then apply low force, and if surface is not glass, then find out the thickness. Whether it is thick, then you can have the high force, and if it is thin, then you can have the low force. Next, let us look at the last topic here in this lecture, that is asymptotic analysis and big O notation. This concept is used in evaluating the time a software takes to execute. Okay. So, the complexity analysis studies how the number of steps and an algorithm takes, and this is denoted by Tn, and grows as the input size n becomes very large. Instead of measuring runtime on a specific computer, asymptotic analysis provides a hardware independent way to compare the algorithm, which algorithm is taking less time. It focuses on highest order term of, say, here, since the term dominates performance for large inputs. Okay. So, for example, in a robot path planning, say algorithm A, Tn is say 100 n plus 1000, it is a linear in n, right. So, we can write it as big O n. But suppose if you have algorithm B where it is Tn is n square plus 1, so we can see that this is quadratic. Okay. So, this is big O n square, and as the grid size increases, the linear algorithm scores better than the quadratic one, even if it has larger constants. Running time is a measure of the number of operations performed by an algorithm, typically categorized as worst case or average case. In robotics, search algorithm like breadth first search algorithm, which we have just seen, as well as the depth first search and A star are analyzed for their efficiency. A star I have not discussed here, but we will be taking up in the later lecture. BFS is uninformed but guaranteed to find an optimal path in terms of the number of edges, whereas A star uses heuristic to improve the search efficiency. Common running time, say for the linear one you are going to have O of the order n, for the logarithmic one your big O is going to be of the order log n, and for the quadratic one big O is going to be of the order of n square. If you look at a robot navigating a grid using A star algorithm, okay, then the Euclidean distance, it uses Euclidean distance as the heuristic. Okay, the search is more efficient than BFS because it expands fewer nodes, okay, by ignoring directions that move away from the goal. Completeness characterizes whether an algorithm is guaranteed to find a solution if one exists. Okay. Complete always finds a solution in finite time or determines that none exist. Okay. Resolution complete finds a solution if the discretization is small enough, and probabilistically complete, the probability of finding a solution converges to 1 as time approaches infinity. If we are using genetic algorithm or GA for the robot path planning, okay, this is often a probabilistically complete one, and they may find a near optimal path quickly through random mutation, but unlike A star, they do not guarantee finding the absolute shortest path in the finite number of steps. Again, we will be seeing these things when we will be studying the genetic algorithm in detail. So, today we have seen some basic concept of linear algebra, which forms the backbone of robot dynamics and control. We have seen some of the concept of calculus, probability and statistics, which we will be using in our AI part of this course. Then we have seen some control concepts, okay, graph theory and searches, and the complexity analysis. So, these are the references, and if you want to see further details about these topics, you can go through this. Thank you for your attention.